Ok anh em ơi, chào mừng anh em quay trở lại với stream ạ. Thì yeah, chả hát thôi anh ơi. Tiếng đâu rồi? Mất. Wow. Stream mode thì nó không có tiếng Discord. Đây, ok anh em ơi. Thì hôm nay chúng ta sẽ học nha. Học nói chung là chúng ta cần học nhiều đấy, tại vì đây tôi đang nhắm 70 tiếng một tuần và như cậu thấy thì như anh em thấy ấy, thì nó nói chung là hôm nay sẽ 12 tiếng nhá. Chấn chết luôn đây. Hôm nay nhiều. Không ăn, không có nghỉ ngơi gì hết. Chủ chiến đấy. Được rồi, để tôi xem lại việc cần làm. Sẽ là code cho anh em đây. Tôi có luộc cảm biến của lab về nhà để code rồi. Paper. Còn này nữa. Ngày mai thì ôn thi sau nha. Có mấy môn tôi cần ôn thi chứ, đấy là ngày mai. Hôm nay cứ code đây. Hôm nay chỉ code đây. Được rồi. Đấy. Sẽ lắp cảm biến luôn này. Lắp cảm biến luôn đấy. Cái mic mới của tôi nó không dùng cái cổng USB nữa. Đây là, yeah. Rồi, xin chào. Xin chào. Um, xin chào. Đấy thì anh em thấy quỷ vậy. 70 tiếng một tuần nha, 70 tiếng một tuần thì tôi sẽ được tôi đây 70 tiếng một tuần. Đang có một video, nếu mà không phải là cậu tôi nhầm. Em đang thắc mắc là màn hình có cái gì đấy đúng không? Đây phải là thế này mới đúng. Ok, để tôi intro lại nha, ngại quá. Đấy thì hôm nay em thấy tôi muốn học 70 tiếng một tuần nhưng mà tôi mới được 47 tiếng thôi, nên là tôi sẽ nói chung hôm nay sẽ cố 12 tiếng đi, rồi ngày mai nốt 10 tiếng là xong. Hôm nay sẽ code thôi, mai bắt đầu học những cái khác sau. Ok, video chạy là tốt nha. Công nhận đồ đạc cũng ngon ha, trong vị tín thật. Ok, mình đã đây nha, code luôn bắt đầu vào ấy thì code luôn thì nó hơi ấy nhỉ. Chắc sáng sớm xúc miệng một tí đi, một tí tính ra mẹ cái vụ đổi vaccine này hay phết đấy chứ, nó cũng kiểu có nơi mà đi sau. Hay ha. Ây da, ngược sáng quá. Đúng là ngược sáng hơi cái đèn anh em ạ. Cửa sổ trước tôi nó mở, kéo lại chắc là đỡ đen hơn đấy. Ây da, đây này. Rồi, chắc tôi nhầm. Là nó đen phải cái cửa đằng sau ấy. Rồi rồi, không sao. Kênh học tập đèn tị được. Tầm. Nay chắc là học phát cái này đi. Tích nốt nữa nha. Nốt rồi đâu. Đi trong khiếp vậy trời. Thì pha nó tốt. Thì chơi theo sensor. Cái tên gì quên mất tiêu rồi. Nó dính nhỉ, thú vị thật. Thật chứ. Accelerometer là tốt nha. Vuông. Nói chung chưa tìm hiểu kỹ cái này rồi, nên xem một chút mà thôi. Hôm nay tôi muốn refine lại cái đống quỷ này đã. Actor critic. Sáng sớm làm mấy cái sọt này trông đã hơn đấy, còn mấy cái căng thẳng thì tí nữa làm sao nhá, cột các thứ. Ok. Được rồi, được rồi. Nói chung mới stream mà được 2 người vào em cũng show với nhỉ, cũng được đấy nhá. Cái gì vậy? Chị du quýt à? Chị du quýt được không thông báo nhỉ? Nãy tôi restart máy trước khi stream. Ok. Đó. Mà, hồi làm khó hiểu lắm, bây giờ đọc lại dễ hiểu thật. Như chuyên gia à? Re of nó ập lâu hả? Ập gì? Re ập re. Re là trúng số nhiều đúng không nhỉ? Dâu re phát re dâu à, gì đây là số nhiều dâu rồi, gì là số ít dâu dâu re dâu re rồi tre là gì nhỉ? Đi re dâu dâu là gì? Dâu re Rồi. Rồi. Mình giữ nhỉ, cái ngại đọc ấy, form trình bày thì xấu, chữ thì nhiều. If the action space is decreased, biệt hả? Độc lập. Chắc là tôi hiểu. Nó vừa rõ ràng vừa không rõ ràng cùng lúc. Mày thế đó. Gì cũng có mày. Là ảnh mà. Kêu factor mũ T, R mũ T, ý là trông rất dễ hiểu rồi đó. Tôi sẽ chú thích ở đây. Discount factor kia rồi reward thôi. Tức là cái reward xa thì giống cái ấy. Reward. Steady. Thế nó có giống cái ấy không? Hay là giống cái Bellman không? Reward. Nó tổng reward. Solid reward nó giống cái. Từ từ nhé. Aspect tại aspect cộng R tại đấy cộng với cái đằng trước đó thì nó không phải là yên cái này hả? Bellman. À, tức là reverse hả? Tức là đây là cái hàm giá trị Đây là trong quá khứ, những cái bước trong quá khứ nó sẽ có cái chỉ số ở đấy. Đây cộng một tức là trong các bước trong tương lai. Các bước trong tương lai nó sẽ kiểu cái này ý nghĩa là cái hay là tốt và nó vừa mới làm sẽ quan trọng hơn. Cái này là cái độ tập trung vào hành động tốt đang làm thay vì những cái hướng đến cái tốt trong tương lai, nhưng mà phải có những cái tốt trong tương lai hả? Rồi từ thế thì Batman là Dot product mà. nút hẳn nhá. Ừ. Ê, nói thật chứ trông to to hơn thì sao? Tôi giới thiệu cho anh em một con video rất hay nói về PPL.
Vẫn thế. Policy thì bạn dùng ratio policy.
Thú vị vậy. Không ai nói gì là tốt nha. Study it good. Be study. Oh my gosh. Rồi, đó, này chắc trôi lâu. Từ thôi. Xem trong câu này tôi đang ghi được những cái gì. Tôi thấy khó hiểu. trông khó hiểu thật đấy. Hôm lúc đầu 2 viewer, giờ không có ai nữa mà. Như thế thỉnh thoảng im lặng tí à? Khó nói. Bóc tới chơi. Ngã trồng phế thật. Ngày ngày này thế lúc hết rồi. Thế đấy. Ôi. Lâu không vào học ý kiến. Tốt này. Chơi con mèo thôi, chơi con mèo thôi. Ôi viewer, hay vậy. Chào viewer nha. Tôi vừa bắt con mèo về. Hay à. Sao? Đây, đi chơi đi. Đây. Không có gì làm đấy. Ok anh em nhá. Tôi xong cốt rồi anh em, sắp rồi. Dọn lại đầu cái này đã. Ừ. Ô, rồi, nghèo hơn chạy là hay rồi. Gradient descent. Bias variance. Không có cần thiết. Tôi vãi vậy, thành cái mày. Cả bóng có tốt nha. Cắt bóng cái gì? Hello, tôi cắt cho mèo. Không mèo kia, làm gì đây? Nhổng vít đây. Hả? Gì mày? Hả? Hả? Ra đây cắt bóng này. Ra đây. Được rồi, giờ đi. Trời. Sao mình ghi nhiều thứ nhỉ? Ok ok nhá. Viewer mà hay thật. Thật quý. Được rồi. Một cái là kỹ thuật để mà debug, một cái là kỹ thuật là triển khai. Next normalization đây mà. Rescale. Còn cái gì đây? À, cái này hả? Mẹ rồi, mình viết cái gì đây? September. Wow. con mèo đó. Đi đâu vậy? Đi lại đây, nào đây. Đúng rồi, nằm xuống. Tốt. Nằm là tốt nha. Con sâu. Đi đâu con sâu? Đâu ra? Sao nằm đây? Đâu ra? Nằm đây rồi. Nó làm gì? À, đòi ra ngoài. Thôi, đi cho đi. Chắc chỉ một hai con mèo. Dạ, đi nhận. Thật. Ôi ơi. Sao vào đây? Thật nào? Ừ.
Anh đi nhặt cho em. Mẹ cho em đi ăn.
Nóng quá. thế gom giờ ăn vào với giờ học là tốt nha. Muốn đủ KPI thì phải gom giờ ăn vào giờ học anh em. Đang refine nốt cái nốt này, đã refine cái nốt bao lâu? Tôi phát 2 tiếng. Dạ học là A2C các thứ, nhưng mà nói chung cũng hơi hơi ấy đấy. Nhanh nha. Không quỳ hết. Ok.
Hello and welcome back. This week, the first thing we'll do is show you a number of case studies of effective convolutional neural networks. So why look at case studies? Last week, we learned about the basic building blocks, such as convolutional layers, pooling layers, and fully connected layers of confidence. It turns out a lot of the past few years of computer vision research has been on how to put together these basic building blocks to form effective convolutional neural networks. And one of the best ways for you to gain intuition yourself is to see some of these examples. I think just as many of you might have learned to write code by reading other people's code, I think that a good way to gain intuition how to build confidence is to read or to see other examples of effective confidence. And it turns out that a neural network architecture that works well on one computer vision task often works well on other tasks as well, such as maybe on your task. So if someone else has trained a neural network, has figured out a neural network architecture that's very good at recognizing cats and dogs and people, but you have a different computer vision task, like maybe you're trying to build a self-driving car, you might well be able to take someone else's neural network architecture and apply that to your problem. And finally, after the next few videos, you'll be able to read some of the research papers from the field of computer vision, and I hope that you might find it satisfying as well. You don't have to do this as a class, but I hope you might find it satisfying to be able to read some of these seminal computer vision research paper and see yourself able to understand them. So with that, let's get started. As an outline for what we'll do in the next few videos, we'll first show you a few classic networks. The Net 5 network, which came from, I guess, the 1980s, AlexNet, which is often cited, and the VGG network. And these are examples of pretty effective neural networks, and you see ideas from these papers that will probably be useful for your own work as well. Then I want to show you the ResNet, or called residual network. And you might have heard that neural networks are getting deeper and deeper. The ResNet neural network trained a very, very deep 152-layer neural network that has some very interesting tricks, interesting ideas how to do that.
Itu là em tôi đang hỏi ăn gì, một cái option cho sao bầu tầm 5 phút à, rồi xem có gì ngon. Đây. Thứ này có quả áo dài tay đẹp nhất mà tôi chả có keo dài tay. Ship à. Cuốn cái chăn thì nó mất có điểm. Ai. Rồi, hay vô luôn mà. Ok nha.
Do that effectively. And then
Ê, mấy cái này tôi biết này.
finally, you
Này,
also
hay
see
nha.
a case study of the inception neural network. After seeing these neural networks, I think you have much better intuition about how to build it.
Ok, đang sắp sâu case study.
In this video, you learn about dimensions reducers from reducing by 6 over, and the net 5 was 32 by 32 by 1. Let's take a look.
Ok.
Here's the Linet 5 architecture. You start off with an image
file là
which,
tốt nha.
say 32 by 32 by 1. And the goal of Linet 5 was to recognize handwritten digits. So maybe an image
Handwritten.
of a digit like that. And Linet 5 was trained on grayscale images, which is why it's 32 by 32 by 1. This neural network architecture is actually quite similar to the last example you saw last week. In the first step, you use a set of 6 5x5 filters with a stride of 1. Because you use 6 filters, you end up with a 28 by 28 by 6 over there. And with a stride of 1 and no padding, the image dimensions reduces from 32 by 32 down to 28 by 28. Then the Linet neural network applies pooling. And back then, when this paper was written, people used average pooling much more. If you're building a modern variant, you probably use max pooling instead. But in this example, you average pool, and with a filter width of 2 and a stride of 2, you wind up reducing the dimensions, the height and width, by a factor of 2. So you now end up with a 14 by 14 by 6 volume. I guess the height and width of these volumes aren't entirely drawn to scale. Now, technically, if I were drawing these volumes to scale, the height and width would be shrunk by a factor of 2. Next, you apply another convolutional layer. This time, you use a set of 16 filters. So it's 5x5, so you end up with 16 channels in the next volume. And back when this paper was written in 1998, people didn't really use padding, or you're always using valid convolutions, which is why every time you apply a convolutional layer, the height and width shrinks. So that's why here you go from 14 by 14 down to 10 by 10. Then another pooling layer, so that reduces the height and width by a factor of 2, and you end up with 5 by 5 over here. And if you multiply out these numbers, 5 by 5 by 16, this multiplies out to 400, right? That's 25 times 16 is 400. And the next layer is then a fully connected layer that fully connects each of these 400 nodes with every one of 120 neurons. So there's a fully connected layer. And sometimes I would draw out explicitly a layer with 400 nodes. Well, I'm skipping that here. There's a fully connected layer, and then another fully connected layer. And then the final step is it uses these essentially 84 features and uses it with one final output. I guess you could draw one more node here to make a prediction for y hat. And y hat took on 10 possible values corresponding to recognizing each of the digits from 0 to 9. A modern version of this neural network would use a softmax layer with a 10-way classification output, although back then, Linet 5 actually used a different classifier at the output layer, one that's used less today. So this neural network was small by modern standards, had about 60,000 parameters. And today you often see neural networks with anywhere from 10 million to 100 million parameters, and it's not unusual to see networks that are literally about 1,000 times bigger than this network. But one thing you do see is that as you go deeper in the network, so as you go from left to right, the height and width tend to go down. So you went from 32 by 32 to 28 to 14 to 10 to 5, whereas the number of channels tends to increase. It goes from 1 to 6 to 16 as you go deeper into the layers of the network. One other pattern you see in this neural network that's still often repeated today is that you might have one or more conv layers followed by a pooling layer, and then one or sometimes more than one conv layer followed by a pooling layer, and then some fully connected layers, and then the output. Right? So this type of arrangement of layers is quite common. Now finally, this is maybe only for those of you that want to try reading the paper. There are a couple other things that were different. The rest of this slide, I'm going to make a few more advanced comments, only for those of you that want to try to read this classic paper. And so everything I'm going to write in red, you can safely skip on this slide. And there's maybe an interesting historical footnote that is okay if you don't follow fully. So it turns out that if you read the original paper, back then people used sigmoid and tanh nonlinearities, and people weren't using ReLU nonlinearities back then. So if you look at the paper, you see sigmoid and tanh referred to. And there were also some funny ways about this network was wired, at least funny by modern standards. So for example, you've seen how if you have a NH by NW by NC network with NC channels, then you use F by the same NC dimensional filter, where every filter looks at every one of these channels. But back then, computers were much slower, and so to save on computation as well as on parameters, the original Linet 5 had some crazy complicated way where different filters look at different channels of the input block. And so the paper talks about those details, but the more modern implementation, wouldn't have that type of complexity these days. And then one last thing that was done back then, I guess, but isn't really done right now, is that the original Linet 5 had a nonlinearity after pooling. Right? And I think it actually used a sigmoid nonlinearity after the pooling layer. So if you do read this paper, and this is one of the harder ones to read, the ones we'll go over in the next few videos. The next one might be an easier one to start with. Most of the ideas on this slide are described in sections 2 and 3 of the paper, and later sections of the paper talk about some other ideas. It talks about something called the graph transformer network, which isn't widely used today. So if you do try to read this paper, I recommend focusing on section 2, which talks about this architecture, and maybe take a quick look at section 3, which has a bunch of experimental results, which are pretty interesting. The second example of a neural network I want to show you is AlexNet, named after Alex Krzyzewski, who was the first author of the paper describing this work. The other authors were Ilya Sutskever and Jeffrey Hinton. So AlexNet input starts with 227 by 227 by 3 images. Oh, and if you read the paper refers to 224 by 224 by 3 images. But if you look at the numbers, I think that the numbers make sense only if it's actually 227 by 227. And then the first layer applies a set of 96 11 by 11 filters with a stride of 4. And because it uses a large stride of 4, the dimension shrinks to 55 by 55. So roughly going down by a factor of 4 because of the large stride. And then it applies max pooling with a 3 by 3 filter, so f equals 3 and a stride of 2. So this reduces the volume to 27 by 27 by 96. And then it performs a 5 by 5 same convolution, so with padding. So you end up with 27 by 27 by 276. Max pooling again, this then reduces the height and width to 13. And then another same convolution, so same padding. So it's 13 by 13 by now 384 filters. And then 3 by 3, same convolution again, gives you that. Then 3 by 3, same convolution gives you that. Then max pool brings it down to 6 by 6 by 256. If you multiply out these numbers, 6 times 6 times 256, that's 9,216. So we're going to unroll this into 9,216 nodes. And then finally, it has a few fully connected layers. And then finally, it uses a softmax to output which one of 1,000 classes the object could be. So this neural network actually had a lot of similarities to Linet, but it was much bigger. So whereas Linet, or Linet 5 from the previous slide, had about 60,000 parameters, this AlexNet had about 60 million parameters. And the fact that it could take pretty similar basic building blocks, but have a lot more hidden units and train it on a lot more data, say trained on the ImageNet dataset, that allowed it to have this remarkable performance. Another aspect of this architecture that made it much better than Linet was using the ReLU activation function. And then again, just if you read the paper, some more advanced details that you don't really need to worry about if you don't read the paper. One is that when this paper was written, GPUs were still a little bit slower, so it had a complicated way of training on 2 GPUs. And the basic idea was that a lot of these layers was actually split across 2 different GPUs, and there was a thoughtful way for when the 2 GPUs would communicate with each other. And the paper also, the original AlexNet architecture also had another type of layer called a local response normalization. And this type of layer isn't really used much, which is why I didn't talk about it. But the basic idea of local response normalization is if you look at one of these blocks, one of these volumes that we have on top, let's say for the sake of argument, this one, 13 by 13 by 256. What local response normalization, LRN, does is it'll look at one position, so one position height and width, and look down this across all the channels, look at all 256 numbers and normalize them. And the motivation for this local response normalization was that for each position in this 13 by 13 image, maybe you don't want too many neurons with a very high activation. But subsequently, many researchers have found that this doesn't help that much. So this is one of those ideas that I guess I'm drawing in red because it's less important for you to understand this one. And in practice, I don't really use local response normalizations really in the networks that I would train today. So if you're interested in the history of deep learning, I think even before AlexNet, deep learning was starting to gain traction in speech recognition and a few other areas. But it was really this paper that convinced a lot of the computer vision community to take a serious look at deep learning, to convince them that deep learning really works in computer vision. And then it grew on to have a huge impact, not just in computer vision, but beyond computer vision as well. And if you want to try reading some of these papers yourself, and you really don't have to for this course, but if you want to try reading some of these papers, this one is one of the easier ones to read, so this might be a good one to take a look at. So whereas AlexNet had a relatively complicated architecture, there's just a lot of hyperparameters, right, where you have all these numbers that Alex Krzyzewski and his co-authors had to come up with. Let me show you a third and final example in this video called the VGG or the VGG16 network. And a remarkable thing about the VGG16 network is that they said instead of having so many hyperparameters, let's use a much simpler network where you focus on just having conv layers that are just 3 by 3 filters with a stride of 1 and always use the same padding, and make all your max pooling layers 2 by 2 with a stride of 2. And so one very nice thing about the VGG network was it really simplified these neural network architectures. So let's go through the architecture. So you start off with an image, and then the first 2 layers are convolutions, which are therefore these 3 by 3 filters. And in the first 2 layers, you use 64 filters. So you end up with a 224 by 224 because you're using same convolutions, and then with 64 channels. So because VGG16 is a relatively deep network, I'm going to not draw all the volumes here. So what this little picture denotes is what we would previously have drawn as this 224 by 224 by 3, and then a convolution that results in, I guess, a 224 by 224 by 64. So drawn as a deeper volume, and then another layer that results in, 224 by 224 by 64. So this conv 64 times 2 represents that you're doing 2 layers, 2 conv layers with 64 filters. And as I mentioned earlier, the filters are always 3 by 3 with a stride of 1, and they're always the same convolutions. So rather than drawing all these volumes, I'm just going to use text to represent this network. Next, then uses a pooling layer. So the pooling layer will reduce, and think about it, goes from 224 by 224 down to what? Right, goes to 112 by 112 by 64. And then it has a couple more conv layers. So this means it has a 128 filters. And because it's the same convolutions, let's see, what's the new dimension? Right, it'll be 112 by 112 by 128. And then pooling layer, so you can figure out what's the new dimension, right? So it'll be that. And now 3 conv layers with 256 dimensional filters, with 256 filters, sorry. Then a pooling layer, and then a few more conv layers, pooling layer, more conv layers, pooling layer. And then it takes this final 7 by 7 by 5, 12, feeds into a fully connected layer, fully connected with 4,096 units, and then the softmax output 1 over 1,000 classes. By the way, the 16 in the name VGG16 refers to the fact that this has 16 layers that have weights. And this is a pretty large network. This network has a total of about 138 million parameters. And that's pretty large, even by modern standards. But the simplicity of the VGG16 architecture made it quite appealing. You can tell its architecture is really quite uniform. There's a few conv layers followed by a pooling layer, which reduces the height and width. Right? So the pooling layers reduce the height and width. You have a few of them here. But then also, if you look at the number of filters in the conv layers, here you have 64 filters, and then you double to 128, double to 256, double to 512. And then I guess the author's factor was big enough and didn't double it again here. But this, sort of roughly doubling on every step, or doubling through every stack of conv layers was another simple principle used to design the architecture of this network. And so I think the relative uniformity of this architecture made it quite attractive to researchers. The main downside was that it was a pretty large network in terms of the number of parameters you had to train. Oh, and if you read the literature, you sometimes see people talk about VGG19. That's an even bigger version of this network. And you can see the details in the paper cited at the bottom by Karen Simeryan and Andrew Zisserman. But because VGG16 does almost as well as VGG19, a lot of people will use VGG16. But the thing I liked most about this was that this made this pattern of how, as you go deeper, height and width goes down. It just goes down by a factor of 2 each time with the pooling layers, whereas the number of channels increases. And here it, roughly goes up by a factor of 2 every time you have a new set of conv layers. So by making the rate at which these go down and that go up very systematic, I thought this paper was very attractive from that perspective. So that's it for the 3 classic architectures. If you want, you should go and now read some of these papers. I recommend starting with the AlexNet paper, followed by the VGGNet paper, and then the Linnet paper is a bit harder to read, but it is a good classic. You want to take a look at that. But next, let's go beyond these classic networks and look at some even more advanced, even more powerful neural network architectures. Let's go on to the next video.
Hai.
Very, very deep neural networks are difficult to train because of vanishing and exploding gradients types of problems. In this video, you learn about skip connections, which allows you to take the activation from one layer and suddenly feed it to another layer even much deeper in the neural network. And using that, you're going to build ResNets, which enables you to train very, very deep networks, sometimes even networks of over 100 layers. Let's take a look. ResNets are built out of something called a residual block. Let's first describe what that is. Here are 2 layers of a neural network where you start off with some activation in layer L, then you go to AL plus 1, and then the activation 2 layers later is AL plus 2. So to go through the steps in this computation, you have AL, and then the first thing you do is you apply this linear operator to it, which is governed by this equation to go from AL to compute ZL plus 1 by multiplying by the weight matrix and adding that bias vector. After that, you apply the ReLU nonlinearity to get AL plus 1, and that's governed by this equation where AL plus 1 is G of ZL plus 1. Then in the next layer, you apply this linear step again, so it's governed by that equation, right? So this is quite similar to this equation we saw on the left. And then finally, you apply another ReLU operation, which is now governed by that equation, where G here would be the ReLU nonlinearity. And this gives you, AL plus 2. So in other words, for information from AL to flow to AL plus 2, it needs to go through all of these steps, which I'm going to call the main path of this set of layers. In a residual net, we're going to make a change to this. We're going to take AL and just fast forward it, copy it much further into the neural network to here, and just add AL before applying the nonlinearity, the ReLU nonlinearity. And I'm going to call this the shortcut. So rather than needing to follow the main path, the information from AL can now follow a shortcut to go much deeper into the neural network. And what that means is that this last equation goes away, and we instead have that the output AL plus 2 is the ReLU nonlinearity G applied to ZL plus 2 as before, but now plus AL. So the addition of this AL here, it makes this a residual block. And in pictures, you can also modify this picture on top by drawing this shortcut to go here. And we're going to draw it as going into this second layer here, because the shortcut is actually added before the ReLU nonlinearity. So each of these nodes here, right, that applies a linear function and a ReLU. So AL is being injected after the linear part, but before the ReLU part. And sometimes instead of the term shortcut, you also hear the term skip connection. And that refers to AL just skipping over a layer, or kind of skipping over almost 2 layers in order to pass this information deeper into the neural network. So what the inventors of ResNet, so that would be Kai Ming-he, Xiang Yujian, Shaoqing Ren, and Jian Seng, what they found was that using residual blocks allows
Whoa.
inventors of ResNet, so that would be
Carmen thì đó, cái thằng này, anh bạn này có quà Init à?
Kai Ming-he, Xiang Yujian, Shaoqing Ren, and Jian Seng. What they found was that
Hay gì hay mà
using
phát
residual
minh ra
blocks
xong rồi
allows
đặt
you
tên.
to train much deeper neural networks. And the way you build a ResNet is by taking many of these residual blocks like these, and stacking them together to form a deep network. So let's look at this network. This is not a residual network. Let's call this a plane network. This is the terminology of the ResNet paper. To turn this into ResNet, what you do is you add all those skip connections, or those short circuit connections, like so. So every 2 layers ends up with that additional change that we saw on the previous slide to turn each of these into a residual block. So this picture shows 5 residual blocks stacked together, and this is a residual network. And it turns out that if you use a standard optimization algorithm, such as gradient descent or one of the fancy optimization algorithms to train a plane network, so without all the extra without all the extra shortcuts or skip connections I just drew in, empirically you find that as you increase the number of layers, the training error will tend to decrease after a while, but then it'll tend to go back up. And in theory, as you make a neural network deeper, it should only do better and better on the training set, right? So in theory, having a deeper network should only help. But in practice or in reality, having a plane network, so not a ResNet, but having a plane network that's very deep means that your optimization algorithm just has a much harder time training. And so in reality, your training error gets worse if you pick a network that's too deep. But what happens with ResNets is that even as the number of layers gets deeper, you can have the performance of the training error kind of keep on going down. Even if we train a network with over 100 layers, and there are now some people experimenting with networks that are over 1,000 layers, although I don't see that used much in practice yet. But by taking these activations, be it X or these intermediate activations, and allowing it to go much deeper in the neural network, this really helps with the vanishing and exploding gradient problems and allows you to train much deeper neural networks without really appreciable loss in performance. And maybe at some point, this will plateau, this will flatten out, and it doesn't help that much deeper and deeper networks. But ResNet has certainly been effective at helping train very deep networks. So you've now gotten an overview of how ResNets work. And in fact, in this week's programming exercise, you get to implement these ideas and see it work for yourself. But next, I want to share with you better intuition or even more intuition about why ResNets work so well. Let's go on to the next video. So why do ResNets work so well? Let's go through one example that illustrates why ResNets work so well, at least in the sense of how you can make them deeper and deeper without really hurting your ability to at least get them to do well on the training set. And hopefully, as you've understood from the third course in the sequence, doing well on the training set is usually a prerequisite to doing well on your holdout or on your dev or on your test sets. So being able to at least train a ResNet to do well on the training set is a good first step toward that. Let's look at an example. What we saw in the last video was that if you make a network deeper, it can hurt your ability to train the network to do well on the training set. And that's why sometimes you don't want a network that is too deep. But this is not true, or at least it's much less true when you're training a ResNet. So let's go through an example. Let's say you have X feeding into some big neural network, and this outputs some activation AL. Let's say for this example that you're going to modify the neural network to make it a little bit deeper. So you do the same big N, and this outputs AL. And we're going to add a couple extra layers to this network. So let's add one layer there and another layer there. And this will output AL plus 2. Only let's make this a ResNet block, a residual block, with that extra shortcut. And for the sake of argument, let's say throughout this network, we're using the ReLU activation function. So all the activations are going to be greater than or equal to 0, with the positive exception of the input X. Right, because the ReLU activation outputs numbers either 0 or positive. Now let's look at what AL plus 2 will be. To copy the expression from the previous video, AL plus 2 will be ReLU applied to ZL plus 2 and then plus AL, where this addition of AL comes from the short circuit or from the skip connection that we just added. And if we expand this out, this is equal to G of WL plus 2 times A of L plus 1 plus BL plus 2. So that's ZL plus 2 is equal to that, plus AL. Now notice something. If you're using L2 regularization or weight decay, that will tend to shrink the value of WL plus 2. If you're applying weight decay to B, that will also shrink this, although I guess in practice, sometimes you do and sometimes you don't apply weight decay to B. But W is really the key term to pay attention to here. And if WL plus 2 is equal to 0, and let's say for the sake of argument that B is also equal to 0, then these terms go away because they're equal to 0, and then G of AL, this is just equal to AL, right? Because we assumed we're using the ReLU activation function, and so all the activations are non-negative, and so G of AL is the ReLU applied to a non-negative quantity, so you just get back AL. So what this shows is that the identity function is easy for residual block to learn, and it's easy to get AL plus 2 equal to AL because of this skip connection. And what that means is that adding these two layers to a neural network, it doesn't really hurt your neural network's ability to do as well as this simpler network without these two extra layers, because it's quite easy for it to learn the identity function, to just copy AL to AL plus 2 despite the addition of these two layers. And this is why adding two extra layers, adding this residual block to the somewhere in the middle or to the end of this big neural network, it doesn't hurt performance. But of course, our goal is to not just not hurt performance, is to help performance. And so you can imagine that if all of these hidden units, if they actually learn something useful, then maybe you can do even better than learning the identity function. And what goes wrong in very deep plane nets, in very deep networks without these residual, these skip connections, is that when you make the network deeper and deeper, it's actually very difficult for it to choose parameters that learn even the identity function, which is why a lot of layers end up making your result worse rather than making your result better. And I think the main reason the residual network works is that it's so easy for these extra layers to learn the identity function that you're kind of guaranteed that it doesn't hurt performance. And then, a lot of the time you maybe get lucky and it even helps performance. Or at least it's easier to go from a decent baseline of not hurting performance, and then gradient descent can only improve the solution from there. So one more detail, the residual network that's worth discussing, which is through this making your connection in the identity. Our goal is quite easy for it to, and what that means is, and so G of AL is the relative here. And if we expand this out, this is equal to G of WL plus 2 times A of L plus 1 plus BL plus 2, so that's ZL plus 2 is equal to that, plus AL. Now notice something, if you're using L2 regularization or weight decay, that will tend to shrink the value of WL plus 2. If you're applying weight decay to B, that will also shrink this, although I guess in practice, sometimes you do and sometimes you don't apply weight decay to B. But W is really the key term to pay attention to here. And if WL plus 2 is equal to 0, and let's say for the sake of argument that B is also equal to 0, then these terms go away because they're equal to 0, and then G of AL, this is just equal to AL, right? Because we assumed we're using the ReLU activation function, and so all the activations are non-negative, and so G of AL is the ReLU applied to a non-negative quantity, so you just get back AL. So what this shows is that the identity function is easy for a residual block to learn, and it's easy to get AL plus 2 equal to AL because of this skip connection. And what that means is that adding these two layers to a neural network, it doesn't really hurt your neural network's ability to do as well as this simpler network without these two extra layers, because it's quite easy for it to learn the identity function, to just copy AL to AL plus 2 despite the addition of these two layers. And this is why adding two extra layers, adding this residual block to the somewhere in the middle or to the end of this big neural network, it doesn't hurt performance. But of course, our goal is to not just not hurt performance, is to help performance. And so you can imagine that if all of these hidden units, if they actually learn something useful, then maybe you can do even better than learning the identity function. And what goes wrong in very deep
Tôi
nets,
hiểu
in
rồi.
very deep networks without these
Này.
residual, these skip connections, is that when you make the network deeper and deeper, it's actually very difficult for it to choose parameters that learn even the identity function, which is why a lot of layers end up making your result worse rather than making your result better. And I think the main reason the residual network works is that it's so easy for these extra layers to learn the identity function that you're kind of guaranteed that it doesn't hurt performance. And then, a lot of the time you maybe get lucky and it even helps performance. Or at least it's easier to go from a decent baseline of not hurting performance, and then gradient descent can only improve the solution from there. So one more detail in the residual network that's worth discussing, which is through this addition here, we're assuming that ZL plus 2 and AL have the same dimension. And so what you see in ResNets is a lot of use of same convolutions, so that the dimension of this is equal to the dimension, I guess, of this layer or of the outputs layer. So they can actually do this short circuit connection, because the same convolution preserves dimensions, and so it makes it easier for you to have this short circuit and then carry out this addition of two equal dimension vectors. In case the input and output have different dimensions, so for example, if this is 128 dimensional and Z, or therefore AL, is 256 dimensional, as an example, what you would do is add an extra matrix, we call that WS over here, and WS in this example would be a 256 by 128 dimensional matrix. So then WS times AL becomes 256 dimensional, and this addition is now between two 256 dimensional vectors. And there are a few things you could do with WS. It could be a matrix of parameters to be learned. It could be a fixed matrix that just implements zero padding, so it takes AL and then zero pads it to be 256 dimensional, and either of those versions, I guess, could work. So finally, let's take a look at ResNets on images. So these are images I got from the paper by He et al. This is an example of a plane network, and in which you input an image and then have a number of conv layers until eventually you have a softmax output at the end. To turn this into a ResNet, you add those extra skip connections. And I'll just mention a few details. There are a lot of 3x3 convolutions here, and most of these are 3x3 same convolutions. And that's why you're adding equal dimension feature vectors. So rather than a fully connected layer, these are actually convolutional layers, but because they are same convolutions, the dimension is preserved. And so the ZL plus 2 plus AL addition makes sense. And similar to what you've seen in a lot of networks before, you have a bunch of convolutional layers, and then there are occasionally pooling layers as well, or pooling-like layers. And whenever one of those things happen, then you need to make an adjustment to the dimension, which we saw on the previous slide you can do with the matrix WS. And then, as is common in these networks, you have conv pool, and then at the end, have a fully connected layer that then makes a prediction using a softmax. So that's it for ResNets. Next, there's a very interesting idea behind using neural networks with one-by-one filters, one-by-one convolutions. So what good is a one-by-one convolution? Let's take a look at the next video. In terms of designing content architectures, one of the ideas that really helps is using a one-by-one convolution. Now,
Right.
you might be wondering, what does a one-by-one convolution do? Isn't that just multiplying by a number? That seems like a funny thing to do. Turns out it's not quite like that. Let's take a look.
Đấy.
Here's a
Thế rồi
one-by-one
vừa mới
filter.
chửi xong thì
Put the number
người ta
2
nhắc
there.
rồi.
And if you take this 6x6 image, 6x6 by 1, and convolve it with this 1 by 1 filter, you
Bro.
end up just taking the image and multiplying by 2. So 1, 2, 3, and
Ok, thế thì chắc
2,
là vô ích.
4, 6, and so on. And so a convolution by a 1-by-1 filter doesn't seem particularly useful. You just multiply it by some number. but that's the case of 6 by 6 by 1 channel images. If you have
Ờ,
a 6 by 6 by 32 instead of by 1, then a convolution with a 1 by 1 filter can do something that makes much more sense. And in particular,
ok.
what a 1 by 1
Ờ,
convolution will do is it will look at
quên.
each of the 36 different positions here, and it will take
Nhưng
the
mà
element-wise product between
nó một
32
like
numbers on the
nghĩ hay
left
mà nó.
and the 32 numbers in the filter, and then apply a
À,
value nonlinearity to
đây
it.
là number line
So to
có
look at
thằng
one of the 36 positions, maybe one slice through this
theo slide.
volume, you take these 36 numbers, multiply it by, one by one slice through the volume like that, and you end up with a single real number, which then gets plotted in one of the outputs like that. And in fact, one way to think about the 32 numbers you have in this 1 by 1 by 32 filter is that it's as if you have one neuron that is taking as input 32 numbers, multiplying each of these 32 numbers in one slice in the same position, height and width, but these 32 different channels, multiplying them by 32 weights, and then applying a Rayleigh nonlinearity to it, and then outputting the corresponding thing over there. And more generally, if you have not just one filter, but if you have multiple filters, then it's as if you have not just one unit, but multiple units that are taking as input all the numbers in one slice, and then building them up into an output that is 6 by 6 by number of filters. So one way to think about a 1 by 1 convolution is that it is basically having a fully connected neural network that applies to each of the 62 different positions. And what this fully connected neural network does is it inputs 32 numbers and it outputs, number of filters outputs. So I guess depending on notation, this is really an NC of O plus 1, if that's the next layer. And by doing this at each of the 36 positions, each of the 6 by 6 positions, you end up with an output that is 6 by 6 by the number of filters. And this can carry out a pretty non-trivial computation on your input volume. And this idea is often called a 1 by 1 convolution, but it's sometimes also called network in network. And it's described in this paper by Minlin, Qiangchen, and Shu.
Từ nhé. Thì là mình miss mất phim téo à. Thế sao cái này nó to to thế nào nhỉ? Thường nó cái này không nhỉ? Nó kiểu như này mà. Nó cũng bé.
Hello, this is our autonomous hydroponic farm. As you can see, we have a container which holds the plant. We have an arm that goes up and down and a saw right here. How this thing works is right here, you see the code. And once you go and click run, it will go and as long as you put your hand right here, it'll go on up all the way back, and then the saw will go and turn on to go and cut the plant. Furthermore, it goes and has the data of temperature and temperature around the system. There is light within the autonomous farm so that you don't have too much algae, and it reports back the humidity as well.
I helped made that too, guys.
Hả? Hả? What the Hả? Tôi có rất nhiều câu hỏi. Le robot mà. Ê.
Hi everyone. So I'm really glad to be here to discuss about robotics. But before I start explaining what is the robot and how at Hugging Face we are making AI for robotics accessible, I would like to take a bit of time to reflect what's going on. Like making AI about robotics.
robotics. Pháp hả? Intern Facebook AI. Về xong cũng phải nghĩ lại thấy intern PhD. Intern PhD ở Facebook. Research. Research. AI. AI. Thú vị nhỉ? Đấy là tiếng Anh cái kỳ quá tôi.
But
tiếng Ấn.
before I start explaining what is the robot and how at Hugging Face we are making AI for they are adopted by people.
People.
Like 10 years ago,
10 years
my
ago.
family didn't know much about what I was doing during my PhD. I was working on
PhD.
visual question answering at the time. It was not working super well. And now, 10 years after, everyone is using LLMs every day. My parents are like literally probing human knowledge with a with a chat interface, and they are finding it very useful, and me including. Like every day, I use LLMs to code. It really, I feel like empowered by this kind of tool. What used to take me maybe 1 week takes me a day. And the latest big thing I'm waiting for is, of course, AI becoming agentic and taking care of some of the complexity of the digital world, like navigating website, buying tickets. I'm procrastinating for a few days. I need to buy a ticket to London to see my friends, and it could be nice to have this AI agent. You just ask it, it does it. And I think it would allow us to really focus on what matters the most for us, like social connection, taking care of people. And what's even more impressive to me is that the same techniques of LLMs and AI agents can now be applied to the physical world through robots. And this literally opens infinite possibilities. And to illustrate that, here is the most advanced AI. So it is Pi Zero. It has been shown before lunch, so and Pi Zero fast as well. So this model, it was trained by Physical Intelligence, a company based in California, and they used polygemma. They fine-tune it not to produce language tokens, but to produce action tokens. They are then detokenized into a sequence of motor angles. And so that's literally it. Tokens in, tokens out. There is no 3D representation or reconstruction or LiDAR or depth. It's just using standard cameras, cheap cameras, and the motor information. And then from, the operator, you can see, it messes a bit with the robot, and you can see that the AI is smart enough to correct and fold the shirt. This kind of tasks were very difficult to automate before. And this is a very simple and general approach because you just need to show a few times the task. So you control the robot. You have actually two arms behind, that you don't see here that allows you to manipulate and fold the shirt. And you can do this for this task, but for any task. And one year ago, we saw this
Con nhà
trend,
có
and we wanted to
không, tôi không
create
ý
at
đấy chứ mà.
Face le robot, an open source
Không, ý là tôi cũng
library
bác nhưng mà
to make AI
tôi đã
for
bác rồi, phải
robotics
cho ai đó nói hay
accessible,
tôi
so
mới nghe được
that
chứ.
all this technique, this technology can go out of the labs and be used at home and by everyone, especially people who are not used to
Không biết do cái này hay hay là
robotics.
do cho kích thích nữa mà xem tình cả người. Quay lại nào.
Yeah.
Cái này tí nữa
And even
để
though the details of the architecture
để ăn trưa cho ngon.
used by this idea of a one-by-one convolution, or this sometimes called network of network idea, has been very influential and has influenced many other neural network architectures, including the inception network, which we'll see in the 28 by 192 volume. If you want to shrink the height and width, you can use a pooling layer, so we know how to do that. But what if the number of channels has gotten too big and you want to shrink that? Two filters, this is a filter, has 32 volume. So this is the width of these volumes. And but of course, if you want to keep the number of channels at 192, that's fine too. And the effect of a one-by-one convolution is it just adds nonlinearity. It allows you to learn a more complex function of your network by adding another layer that inputs 20 by 20 by 192 and it allows it to be used.
Rồi.
When designing a layer for a ConvNet, you might have to pick, do you want a 1x3 filter or 3x3 or 5x5, or do you want a pooling layer? What the inception network does is it says, why don't you do them all? And this makes the network architecture more complicated, but it also works remarkably well. Let's see how this works. Let's say for the sake of example that you have inputs a 28 by 28 by 192 dimensional volume. So what the inception network, or what an inception layer says is, instead of architecture more complicated, but it also works remarkably well. Let's see how this works. Let's say for the, do you want a 1x3 filter or 3x3 or 5x5, or do you want a pooling layer? What the inception network does is it says, why don't you do them all? And this makes the network architecture more complicated, but it also works remarkably well. Let's see how this works. Let's say for the sake of example that you have inputs a 28 by 28 by 192 dimensional volume. So what the inception network, or what an inception layer says is, instead of choosing what filter size you want in a conv layer, or even do you want a convolutional layer or pooling layer, let's do them all. So what if you can use a 1x1 convolution, and that will output a 28 by 28 by something. Let's say 28 by 28 by 64 output, and you just have a volume there. But maybe you also want to try a 3x3, and that might output a 28 by 28 by 128. And then what you do is just stack up this second volume next to the first volume, and to make the dimensions match up, let's make this a same convolution. So the output dimension is still 28 by 28, same as the input dimension in terms of height, but 28 by 28 by, in this example, 128. And maybe you might say, well, I want to hedge my bets. Maybe a 5x5 filter works better, so let's do that too, and have that output a 28 by 28 by 32. And again, you use the same convolution to keep the dimensions the same. And maybe you don't want a convolutional layer. Let's apply pooling, and that has some other output, and let's stack that up as well. And here, pooling outputs 28 by 28 by 32. Now, in order to make all the dimensions match, you actually need to use padding for max pooling. So this is an unusual form of pooling, because if you want the input to have height and width 20 by 28 and have the output match the dimension everything else also by 28 by 28, then you need to use same padding as well as a stride of 1 for pooling. So this detail might seem a bit funny to you now, but let's keep going, and we'll make this all work later. But with a inception module like this, you can input some volume and output, in this case, because if you add up all these numbers, 32 plus 32 plus 128 plus 64, that's equal to 256. So you would have one inception module input 28 by 28 by 192 and output 28 by 28 by 256. And this.
Rồi, xin chào, hay quá. Tí nữa là tôi sẽ chỉ code nha, phần code bây giờ tôi đang ý là mới dậy ấy, thì làm một tí ấy cho nó năng lượng, tí video xem. Ý là đây, tôi đang có KPI học được 70 tiếng một tuần. Còn 20 tiếng nữa. Và nói chung là hôm nay tôi cần 10 tiếng nữa. Và để 10 tiếng nữa tôi sẽ hợp nhất thời gian ăn vào thời gian học. Đây, nên tôi đã để dành cái video về robot trông khá hay này để tí ăn xem. Cái này chắc nên limit lại, là bây giờ chưa có nhiều người sử dụng lắm. Khi nào tầm nhiều người dùng thì limit lại thành công nhận đông vui nhỉ. Gần 10 rồi đấy. Trời ơi, cái server mẹ 20 thằng, 10 thằng dùng, khó nói. Nào 10 thằng tôi code tôi limit lại. Có những điều mà chưa ngờ tới, ví dụ như có trên 10 người học. Cái đấy hồi tôi bắt đầu code tôi đâu có ngờ tới đâu. Nhưng mà nó sắp xảy ra rồi. Lúc khác chiều nay code cái chung là hôm nay chỉ code thôi nhỉ, rất nhiều code đấy. Rồi ngày mai bắt đầu học những cái khác sau. Ok, see you then.
This is the hard module input 28 by 28 by 192 and output 28 by 28 by 256. And this is the heart of the inception network, which is due to Tristan Zagady, Wei Liu, Yan Tingjia, Pierre Semny, Scott Reed, Dragomir Angelov, Dmitry Erhan, Vincent Van Kook, and Andrew Rabinovich. And the basic idea is that instead of you needing to pick what of these filter sizes or pooling you want and committing to that, you can do them all and just concatenate all the outputs and let the network learn whatever parameters. does it wants to use whatever combinations of these filter sizes it wants into that image. Or if I would add it, you don't want to convolutionate by an unusual form of pooling because you need to use the same padding as was a strata 1 for pooling. Remember the number 120, so you can compare it with what you see on the next slide, 120 million. Here's an alternative architecture for inputting 28 by 20 by 192 and outputting by 1 convolution your final output. So notice the inputting by 20 by 192 and outputting 20 by 20 by 32. you need to do this 22 block 5 by 5 filter, resulting in this block over here. So just focusing on the 5 by 5 part on the previous slide, we had as input a 28 by 20 by 192 block, and you implement a 5 by 5 same convolution with 32 filters to output 20 by 20 by 32. On the previous slide, I had drawn this as a thin purple slice, but I'm just going to draw this as a more normal looking blue block here. So let's look at the computational cost of outputting this 20 by 20 by 32. So you have 32 filters because the output has 32 channels, and each filter is going to be 5 by 5 by 192. And so the output size is 20 by 20 by 32, and so you need to compute 28 by 28 by 32 numbers. And for each of them, you need to do, this many multiplications, right? 5 by 5 by 192. So the total number of multipliers you need is the number of multipliers you need to compute each of the output values times the number of output values you need to compute. And if you multiply out all these numbers, this is equal to 120 million. And so while you can do 120 million multipliers on a modern computer, this is still a pretty expensive operation. On the next slide, you see how using the idea of one-by-one convolutions, which you learned about in the previous video, you'll be able to reduce the computational cost by about a factor of 10 to go from about 120 million multipliers to about 1/10 of that. So please remember the number 120 so you can compare it with what you see on the next slide, 120 million. Here's an alternative architecture for inputting 20 by 20 by 192 and outputting 20 by 20 by 32, which is following. You're going to input the volume, use a 1-by-1 convolution to reduce the volume to a 16 channels instead of 192 channels. And then on this much smaller volume, run your 5 by 5 convolution to give you your final output. So notice the input and output dimensions are still the same. You input 20 by 20 by 192 and output 20 by 20 by 32, same as the previous slide. But what we've done is we've taken this huge volume we had on the left and we've shrunk it to this much smaller intermediate volume, which is only has 16 instead of 192 channels. Sometimes this is called a bottleneck layer. Right? I guess because a bottleneck is usually the smallest part of something, right? So I guess if you have a glass bottle that looks like this, then this is I guess where the cork goes. Then the bottleneck is the smallest part of this bottle. So in the same way, the bottleneck layer is the smallest part of this network. We shrink the representation before increasing the size again. Now let's look at the computational cost involved. To apply this 1-by-1 convolution, we have 16 filters. Each of the filters is going to be of dimension 1 by 1 by 192. This 192 matches that 192. And so the cost of computing this 28 by 28 by 16 volume is going to be, well, you need this many outputs. And for each of them, you need to do 192 multiplications. I could have written 1 times 1 times 192, right? Which is this. And if you multiply this out, this is 2.4 million. It's about 2.4 million. How about the second? So that's the cost of this first convolutional layer. The cost of this second convolutional layer will be that, well, you have this many outputs, so 20 by 28 by 32, and then for each of the outputs, you have to apply a 5 by 5 by 16 dimensional filter. So 5 by 5 by 16, and you multiply that out is equal to
Hiểu nếu biết. The fuck?
And so the total number of multiplications you need to do is the sum of those, which is 12.4 million multiplications. And you compare this with what we had on the previous slide, you reduce the computational cost from about 120 million multiplies down to about 1/10 of that, to 12.4 million multiplications. Oh, and the number of additions you need to do is about very similar to the number of multiplications you need to do, so that's why I'm just counting the number of multiplications. So to summarize, if you're building a layer of a neural network and you don't want to have to decide, do you want a 1x1 or 3x3 or 5x5 or pooling layer, the inception module lets you say, let's do them all and let's concatenate the results. And then we ran into the problem of computational cost, and what you saw here was how using a 1x1 convolution, you can create this bottleneck layer, thereby reducing the computational costs. Thus, your bottleneck layer, so that when you implement this, hurt the performance of your neural network. It turns out that so long as you implement this bottleneck layer, so that within reason, you can shrink down the representation size significantly, and it doesn't seem to hurt the performance, but saves you a lot of computation. So this is the key of the, these are the key ideas of the inception module. Let's put them together, and in the next video, we'll show you what the full inception network looks like. In the previous video, you've already seen all the basic building blocks of the inception network. In this video, let's see how you can put these building blocks together to build your own inception network. So the inception module takes as input the activation.
Ôi. Ra, nó đi. Nốt cái đống này đi.
This is 28 by 28 by 192, same as our previous video. The
Nó
example
dài đấy.
was the 1 by 1
Nó còn hơn nửa tiếng nữa hả?
layer. So
Sao?
maybe
Nào
the
có
1
ăn
by 1
thì
has 16 channels, and then the 5 by 5 will output a 28 by 28 by, let's say, 32 channels. And this was the example we worked through on the last slide of the previous video. Then to save computation on your 3 by 3 convolution, you can also do the same here. And then the 3 by 3 outputs 28 by 28 by 128. And then maybe you want to consider a 1 by 1, and then finally use the same pattern, 28 by 28 by 256 dimensional output. And channel concat is just, you know, this concatenating. It's really complicated. Here's a picture of the inception network taken from the paper by Zegedi et al. And you notice a lot of repeated blocks in this. Maybe this picture looks really complicated, but if you look at one of the blocks there, that block is basically the inception module that you saw on the previous slide. And subject to little details I won't discuss, you know, this is another inception block, this is another inception block. There's some extra max pooling layers here to change the dimension of the height and width, but that's another inception block. and then there's another max pool here to change the height and width, but basically there's another inception block. But the inception network is just a lot of these blocks that you've learned about repeated to different positions of the network. But so if you understand the inception block from the previous slide, then you understand the inception network. It turns out that there's one last detail to the inception network if you read the original research paper, which is that there are these additional side branches that I just added. So what do they do? Well, the last few layers of the network is a fully connected layer followed by a softmax layer to try to make a prediction. What these side branches do is it takes some hidden layer and it tries to use that to make a prediction. So this is actually a softmax output, and so is that. And this other side branch, again, takes a hidden layer, passes it through a few layers, like a few fully connected layers, and then has a softmax to try to predict what's the output label. And you should think of this as maybe just another detail of the inception network, but what it does is it helps to ensure that the features computed, even in the hidden units, even at intermediate layers, that they're not too bad for predicting the output cost of an image. And this appears to have a regularizing effect on the inception network and helps prevent this network from overfitting. Oh, and by the way, this particular inception network was developed by authors at Google who called it GoogleNet, spelled like that, to pay homage to the LaNet network that you learned about in an earlier video as well. So I think it's actually really nice that the deep learning community is so collaborative, and that there's such strong, healthy respect for each other's work in the deep learning community. Finally, here's one fun fact. Where does the name inception network come from? The inception paper actually cites this meme for "we need to go deeper," and this URL is an actual reference in the inception paper, which links to this image. And if you've seen the movie titled The Inception, maybe this meme will make sense to you, but the authors actually cite this meme as motivation for needing to build deeper neural networks, and that's how they came up with the inception architecture. So I guess it's not often that research papers get to cite internet memes in their citations, but in this case, I guess it works out quite well. So to summarize, if you understand the inception module, then you understand the inception network, which is largely the inception module repeated a bunch of times throughout the network. Since the development of the original inception module, the authors and others have built on it and come up with other versions as well. So there are research papers on newer versions of the inception algorithm, and you sometimes see people use some of these later versions as well in their work, like Inception v2, Inception v3, Inception v4. There's also an inception version that's combined with the ResNet idea of having skip connections, and that sometimes works even better. But all of these variations are built on the basic idea that you learned about in this and the previous video of coming up with the inception module and then stacking up a bunch of them together. And with these videos, you should be able to read and understand, I think, the inception paper, as well as maybe some of the papers describing the later variations as well. So that's it. You've gone through quite a lot of specialized neural network architectures. In the next video, I want to start showing you some more practical advice on how to actually use these algorithms to build your own computer vision system. Let's go on to the next video. Hi, and welcome back. You've learned about the ResNet architecture. You've learned about InceptionNet. In this video,
The fuck. Where? Hello. 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 Ok nha. Tôi bị Hornet, no idea. Ê, cái này hay nha. Tôi xin phép tôi lấy đồ ăn cái xong rồi này. Nhà lấy lên đây rồi mình chiến đấu tiếp thôi. Chắc là tắt cam cho nó nguyên quan điểm. Chứ tôi vẫn học nha. Cái cam tôi là 16:9 đúng không? Full màn hình mà đúng không? Giờ mua hết tên tôi làm cái ảnh 16:9. Ok. Rồi. Cái gì? Tôi vừa dọn cái này. Ok. Thì thế. Thì vào mới đâu? Chỗ này. Màu này. Ừm, nghe không hiểu ý tưởng thì khổ quá, cái này cũng mệt. Ok nhá, tôi xin phép tôi tất cả tôi vẫn học nhé. Hello, hello.
And so the robot, it's a collection of tools. So you have data sets, you have the possibility to host them for free on Hugging Face, to share them, to visualize them online. You also have pre-trained models. So we have Pi0, so you can use it in Python on your laptop. We also have a middleware in Python, very efficient to communicate with a lot of different robots. And a community of 4,000 people on Discord that are very helpful and help us develop this tool. And so to make
Ý là không có năng khiếu record này các bạn, trông hơi khiếp.
make it accessible, we also wanted to develop a kind of full stack project and to develop our own robot arm so that you can get started. So robots before, they were really only in labs. It was super expensive, like $10,000 just for one arm, even more. And now with this simple arm, with $100, you can get one. You can get one. And we design it with Rob Knight from the Robot Studio. And you can order some kits online. So you have the 3D printed parts, you have the motors, and you can assemble it like a Lego. So we have a tutorial online on our GitHub page to train your AI on a simple toy task, just to reproduce a result and validate your setup. So we have the tutorial to assemble. You can do it with a child. And then you can record trajectories with a laptop and phone cameras, and you teleoperate the robot. That's how you you teach it, and then you train it on a MacBook Pro or on a Linux with NVIDIA GPUs. For a while, it can take half an hour, for instance, to start seeing generalization. And then you can evaluate it. You put the blocks. It's a very simple task to grasp a Lego block. You put it in various spaces, and the robot generalizes. It sees from the cameras. If you hide the cameras, it messes up a bit with the robot. But anyway, so that's the kind of thing, like a lot of people from the Discord, every day they send us some videos of them automating tasks at home. And if you assemble two arms, then you can automate more difficult, more challenging chords at home, like the folding clothes, like something that everyone does. But again, this is a setup that costs roughly $400 and not tens of thousands of dollars like it was shown at the beginning of the video. So again, it's using the laptop camera, and on top it's my iPhone. So it really gets you into robotics very fast. And thanks to open source, a lot of people were able to reproduce this and build on top, modify the robots for those who know about robotics. And even we had a very funny contribution where some people attached a Muppet on our arm, and we're using the gripper to make it talk. They connected it to a VLM, and so you really had a language interface, and you had your personal chief Muppet that was there to teach you and help you how to cook things. Pretty practical when you don't know how to cook. And also we organize hackathons. And the last one was in Toulouse. And just over a weekend, people who never touched robotics before, even people who never touched AI, were able to assemble the robots, follow the tutorials, record some trajectories, and automate stuff. So yeah, it's becoming very, very accessible. Also, we work with some students from SIG Robotics Lab from University of Illinois, and we developed together a base and extension with 3 wheels, and we can put any of the arm we developed before on top, and then we can remote control it and teach it many tasks that require a wide range. So we are not that far from having a R2D2 at home that can do some stuff, and also I like it because it's kind of a small object, a bit quirky, and yeah. So you can also order it and build it at home. And this very general approach, tokens in, tokens out, work for more capable robots, like this humanoid robot. It was developed by Pollen Robotics, a startup in Bordeaux. And here, we show that we can discuss with it and ask to grasp for objects and so on. So you can see that if you are in a situation of handicap, it can be very helpful to have this kind of robots. And we had the pleasure to show it to a dog. He was totally impressed. And on the bottom left, you also see Unitree Robots, which is a very important brand right now in humanoids from China. And they are also using low robots to teach their humanoids how to manipulate. And because we really want to explore all the hot topic in robotics right now, we are also building a robot, a humanoid robot arm and hand. It costs like $500. And we developed this very simple glove. It's a kind of exoskeleton that allows us to teleoperate and so to start recording data, how to move the arm of the robot. Yeah, it's quite funny because it works with a system of tendons. We use fishing nets, so it's quite solid. And with very cheap components, you can build those amazing robots that are becoming quite capable. So the next step, of course, is the legs that we are currently building. So yes, build your own robot. Follow us on. You can find all the tutorials on GitHub, and join our community on Discord. I think if you have any question, you will be able to find the solutions. But before I stop my talk, I just wanted to say that I would have never imagined to work on robotics a few years ago. I was really focused on vision and language, but I think that the impact of this technology can be so profound and possibly dramatic if not done right, that we need more people working on this technology. For instance, there are sovereignty concerns and incredible challenges, some like in safety, or some in designing those interfaces, like how we will communicate to those robots. We don't really know yet. With this OpenStem at home, you have, and quite simply applied to robotics. So yeah, it has never been the best time to start, and we are lucky to have this effort here in Paris. So, yeah, I really hope you will join us in our next hackathon. So yeah, thank you for your attention.
Ok, nhạc nhẽo tí nhá.
machines and in our robots. But if I'm being honest, gears are so 3rd century BC, it's time for something different. This project took several months to complete, with tons of prototyping and even more testing. So today I'll be sharing my entire journey in making what I consider to be the most underrated reducer in robotics. So why rope? Well, gears have this little thing called backlash. 3D print them instead of spending a bunch of money on some high precision metal ones. And the benefits of a reducer that I built in this video is called a capstan drive. And the benefits of a capstan drive include being really quiet, having zero backlash, high torque transparency, low inertia, and best of all, being extremely cheap. In fact, all the manufactured components in this video were 3D printed. And besides general strength, there really wouldn't have been any other performance differences if I were to have made them from metal. I decided to prototype my own capstan drive using shoelaces from an old pair of Nikes.
What?
A capstan drive has a smaller drum and a bigger drum. Just like with gears, the reduction ratio is calculated by dividing the big drum diameter by the small drum diameter. The kicker here is that instead of using teeth to transmit torque, a capstan drive uses rope. The rope wraps around the smaller drum and is put into tension on both sides. This way, as the drum spins, one side of the rope gets shorter while the other side gets longer. Now, if you're like me, then you're probably asking, especially why exactly the rope doesn't slip if it's just wrapped around the smaller drum, especially if we were to apply a heavier load. Now, the short answer to this question is because of friction, but the longer answer to this question is still because of friction, but more specifically, something called the capstan equation. Let's say we have rope wrapped around a fixed drum, and let's also say that we can think of T as the person in equilibrium, which equilibrium E to the power of, and theta is the angle of wrap in radians. New constant, T holds for this constant in only Titanics. And what's even, an average person could produce enough force to hold 2 Titanics. And what's even more surprising is that there's still not enough turns in the world that could hold yo mama. The capstan equation shows us why the rope doesn't slip on the small drum. Given the right amount of turns, usually around 5, there's enough friction to prevent slipping with really high loads. In fact, the term capstan refers to a device used on ships to multiply human pulling force when hauling in rope. And the same principle applies to a capstan winch. You can use friction to help you do work. The first device that I plan on making is a capstan actuator. And to do that, I'm using a 90 kV brushless motor and an ODrive S1 controller. This controller uses field-oriented control, which basically turns the brushless motor into a high-precision servo. To make the actuator, I used 1.5mm stainless steel wire instead of shoelaces, threaded 4 screws into the smaller drum to increase its strength, wrapped the wire under the drum instead of over the drum to minimize vertical forces, used a lead screw to tension the wire, and made the gear reduction 8:1 to make it a quasi-direct drive. And just like that, we have our first prototype. The first thing that I noticed was that this thing is smooth like butter. You gotta just watch it run. Looking at a capstan drive, you'll notice that one of its disadvantages is limited rotation. For this reason, I think a capstan drive is best for highly dynamic robots like quadrupeds or bipeds, since those robots don't necessarily need actuators with full rotation. A capstan drive can also be really good for haptic devices. Limited rotation isn't all bad because it means we have physical limits. With physical limits, we can program homing sequences. I programmed 2 different homing sequences. The first one is called 2-stop homing, which moves the actuator to both physical limits, calculates the gear reduction, and then finds the middle position. The second sequence, called 1-stop homing, just goes to one physical limit and uses an already determined gear reduction to find the middle position. In both cases, it's able to detect the physical limits by measuring the current draw of the motor. Now, you may correctly point out that I said the gear reduction is 8:1, and so there really shouldn't be any point of using 2-stop homing since the gear reduction is always known. But for reasons that I still can't understand, when I calculate the reduction in software, it isn't exactly 8:1. It's about 8.5:1. I think in part this has to do with the helical pattern of the smaller drum, but I also tried adding a helical pattern to the bigger drum and still couldn't get an exact 8-to-1 reduction. I ended up just keeping it at 8.5-to-1 and calling it a day. So the purpose of two-stop homing is to calculate the exact gear reduction in software, since we can't use the drum diameters to calculate the gear reduction. I prototyped several different drum designs with different shapes, sizes, and mounting points. Eventually, I settled on one that worked best and moved on to endurance testing. The goal here is to just run the actuator for a long time and see what happens. But unfortunately, just 4 short hours later, the steel wire broke. And to make sure this wasn't a fluke, I ran the test 2 more times, and in both times, it never crossed the 5-hour threshold. Now you may assume that using a thicker cable would solve this problem, but you would be wrong. In fact, a thicker cable would actually be worse. And I know this because of something called a diameter, and as it turns towards the 10.7 steel, so stainless steel wire ratio is much lower. Fortunately, there wasn't any failure this time, so I moved on to load testing, which was when I noticed another issue. With any kind of reducer, you have to consider its life cycle. With gears, you have to worry about wear due to friction over time. And with a capstan drive, you have to worry about creep over time. Creep is the permanent stretch of rope, and this channel is a creep safe zone. No matter what rope it is, if you put it in tension, it will stretch. It's just a matter of how long until it stretches by a significant amount. Unfortunately, a lot of synthetic ropes have higher creep rates than what we would want from a precision actuator. And this is probably what I would consider to be the one major flaw of a capstan drive. It can lose precision by just sitting down over a period of time. So how exactly do we solve this? Well, you'll never guess, but the answer is to just find rope that won't stretch. After reading some academic papers, I found 2 candidates, Vectran and Dyneema DM20. DM20 is a newer rope, and it seems to be the more promising option, since it claims to be the most inextensible rope on the market. It's also almost exclusively sold in Europe, but eventually on time to test just how steel wire, the paracord, the Vectran, and the DM20. I put them into tension and retensioned them over a period of several days. As expected, the paracord was really the only rope that extended significantly over the period of time. Right as I finished that test, the 1-week mark had just passed for the dynamic creep test. The Vectran not only seemed to have extended, but it seemed to have weakened since I could stretch it further by hand. The DM20 seemed to be completely intact with no notable signs of extension. I continued testing with just the DM20 actuator for another week, and it still seemed to be perfectly intact. So DM20 by far and away seems to be the perfect rope to use when it comes to a capstan drive. I was curious about the accuracy of the actuator, so I built a new one with these 10-degree tick marks. This lets me know that the code completes the homing sequence properly and calculates the gear reduction properly. If you're curious about speed, this is how fast it can go. Another important test for any robotic actuator is load testing. I started off by having it sling around 2.5 pounds. I then moved on to 5 pounds, and then I performed a torque test and got around 13 Newton meters. Now a capstan actuator might be fast and precise, but you know what else is fast and precise? Today's sponsor, PCBWay. PCBWay is an online service for all of your machining needs, whether it's CNC machining, 3D printing, sheet metal fabrication, injection molding, and of course, PCB making. What I love most about PCBWay is that for every material they offer, you can find a datasheet explaining everything you need to know about that material to ensure that it best suits your application. You can also view projects that use that exact material if you need a reference. PCBWay has recently introduced UV printing, which allows you to get high-quality images printed on your PCB boards. If you've ever wanted to personalize your boards, then this is the way to do it. Don't let your access to machining hold you back from making your projects. Simply upload your files to PCBWay, receive a quote, and be one step closer to making your projects a reality. You can check out PCBWay today by going to the link in my description. The second device that I'm going to be building is
This is a reminder. Broken hardware, faulty software, and some very questionable design decisions. But at the end of the day, I made something that actually kind of works. All right, let's rewind a little bit. All of this started because I wanted to combine two things that I've made before, an RC car and a quadcopter. From searching online, not many people have done this before, except for a couple universities. So clearly, I needed to do some designing myself. When I design things like this, I like to pour myself a large cup of coffee and then just dive into CAD. CAD stands for Computer Aided Design, and I use a program called Onshape. In Onshape, I can lay out my rough ideas and some sketches just to make sure everything's going to kind of work. For this project, the hardest part was the linkage system, which transforms the vehicle from driving mode to flying mode. This set of linkages holds the wheels and tracks perpendicular to the ground when it's driving. However, just by actuating a servo, the entire body of the vehicle lowers. Then, two linear actuators can be used to pivot the rotors up to be parallel with the ground. Sometimes for unintuitive designs like this, I find that making small 2D models is really useful. This helps me test out different ideas while I'm still early in the design process. Using the dimensions for my small 2D model, and after a couple more hours in CAD fueled by a lot of coffee, I now had a 3-dimensional design which I could actually start building. Most of the parts in this vehicle are actually meant to be 3D printed, which works out great because Bamboo Labs is sponsoring this video. All of the over 100 3D printed parts on this vehicle were printed using their X1 Carbon and P1S printers. And let me tell you, these things are just awesome. I've had these printers for over a year now, and they just work. They're incredibly fast and reliable, and just have really good quality. They've seriously changed the game when it comes to 3D printing. These printers can also print some pretty cool materials like carbon fiber nylon, which is really stiff and extremely lightweight. On this project, I'm using the carbon fiber nylon on some of the parts that need to be stronger and more load-bearing. And then for the rest of the parts, I'm just using some of Bamboo Labs matte PLA filament. Since I'm just using PLA, I made these parts extra strong by adding extra perimeters and infill. This is likely going to increase the weight of the vehicle, but if I need to reduce weight, I can always come back and 3D print them in carbon fiber nylon, which is 20% lighter but almost 3 times as strong. Not to mention the carbon fiber nylon parts have this really cool surface finish, and they're much more heat resistant. Now, to keep the carbon fiber theme going, one of the few non-3D printed parts on this are the side plates. These need to be extremely strong since they basically make up the entire structure of the body. But they also need to look cool, which is equally important. Using my CNC router, I was actually able to cut this carbon fiber body. Is probably for this project is design. Starting off, the servo housing gets assembled, and this is what will actually move. All right, look at this. I found that these type of screws are. All right, so test these arms. Oh yeah, that's so cool. So now why? Why aren't they going? This is a really important part of the design. Once both wheels are installed, and they get attached together using some plastic screws. Treads like this are probably not necessary because it'd be four-wheel drive anyway, but I mean, tracks are awesome, so why not? Time for everybody's favorite thing, electronics. Now this vehicle has 6 brushless motors, 2 servos, and 2 linear actuators, so I need something to control all of this. And that is where this comes in. This is the Teensy 4.0, which is running Dreamflight, which I customized a little bit to run everything. I assembled all these electronics onto a PCB I made for a previous project, which simplifies all the wiring. This PCB also has some headers that break out all the pins, so it's expandable. So I could add the linear actuator controllers on top of it. This control board, as well as a bunch of wires to distribute power, get added to the body we assembled previously. And at this point, we're getting pretty close to being done. Using just a couple bolts, both sets of rotors get added to the main body. Perfect. And then some bolts go in to attach everything. And for the first time, we can see if this thing actually moves correctly. All right, here we go. First ever test. All right, that's driving mode. Now we'll switch it to quadcopter mode. I can't believe how well that works. All right, we know this thing can at least transform the way it's supposed to, but can it drive and fly? Only one way to find out. It can do wheelies. Oh. This thing has way too much power. I was actually really surprised by how well this thing drove. It was super easy to control and it has a ton of power. Sometimes maybe even a little too much power. All right, the real question is though, can this thing actually fly? There's only one way to find out. Now immediately when I tried to transition to flight mode, I knew something was wrong. I tried switching between modes a couple times, but still this thing was just not acting right. Why is this thing acting so weird all of a sudden? Oh! All right, we got problems. I flipped this thing up, and there you go. That actuator is not meant to be cracked in half. Now these are definitely cheap actuators, but also this quad is really heavy, so they're put under a lot of load. So I think the best way to fix this is just by reducing the weight of the quad, which will help it when it flies anyway. I tried to measure how heavy this thing is and it actually overloaded my scale, which is not a good sign. That means it's roughly 3.3 kilograms, which is way too heavy. To fix this weight problem, I started by taking everything apart. I used more of the Bamboo Lab carbon fiber nylon to reprint a bunch of the parts, including the wheels. This stuff is roughly 20% lighter than PLA, and it's even stronger, which is awesome. Now I didn't want this whole thing just to be one color, because it has to look good for YouTube after all. So I reprinted the treads and the actuation arms using this carbon fiber PLA. This is also sold by Bamboo Lab and it's this awesome green color. This stuff is also slightly lighter than normal PLA, and of weight. Odds to kind of be okay, which is huge. And a lot. Let's see if this thing will actually fly. Now entering flying mode. Oh yeah. All right, moment of truth. Oh. Oh. Definitely needs a little more tuning. That was awesome. That worked so much better than I ever thought it would. Now the real test is, will it go back into driving mode? All right, folding. Yes. All right, so finally we got this thing to work. But what's the point? Why even have this thing? Well, imagine this. One day you're driving your quadcopter through the woods, like everyone does, and you come up to a small stream. Both sides are really steep and you can't drive through it. Normally, this might ruin your day. But with this vehicle, all you have to do is transition into flying mode. Then you can just take off and fly right over it. That was terrifying. All right, in all seriousness, even though this thing has been a huge challenge to build, I'm really happy with how it turned out. It looks awesome, and it works really well too. There's a ton more stuff I could try to do with this vehicle, so let me know what you want to see next. If you like this project, you should definitely subscribe to my channel because I have a lot more things like this coming. But that's where I'm going to leave off in this video. So thanks for watching, and I'll see you next time.
Wow, viewer. Hello. Yeah, tôi bán xong á. Là tôi dọn dẹp tí xong rồi học. Thì là tôi vẫn học nãy giờ. Tôi xem những cái thứ bổ ích. Nhưng mà yeah, bây giờ chúng ta sẽ quay trở lại với những thứ code đây. Chiều nay chúng ta sẽ code nha. Tôi nghĩ tôi sẽ xem nốt Unreal tầm nửa tiếng nữa, xong rồi tôi sẽ code. Ok, tôi xin phép tầm 5 phút nha. Anh em nói chuyện về cái ghế nhá. Tôi 5 phút. Dạ. Mày tắt cái chữ đi. Ok. Cái phòng nó ngột ngạt thế nhỉ? Chết rồi anh em ơi. Tình hình là tôi tưởng là nếu vừa học vừa ăn sẽ không buồn ngủ, nhưng mà ôi rồi. Ok, hay rồi nhỉ. Đấy, tôi phải ôi. Trình là gì mà là trình 2 chấm. Ok. Gì chứ? Từ từ nhé, tôi tìm đồ anh em.
Bài nào mình cứ dễ, bài bài nào khó.
Mua bao nhiêu can nhỉ? 50 peso. Bao nhiêu là cúp? Phải tìm được rồi. Trên đó ấy. Mở cửa thoáng thế. Thoáng như mình nhiều mũi.
You learn about MobileNet, which is another foundational convolutional neural network architecture. Use for computer vision. Using MobileNet will allow you to build and deploy neural networks that work even in low compute environments, such as mobile phone. Let's dive in. Why do you need another neural network?
Nói chứ, trong vẫn đang tải ứng. Đây là cái thế pattern thôi. Overfit to a pattern.
network architecture. It turns out a lot of neural networks you've learned about so far are quite computationally expensive. And if you want your neural network to run on a device with less powerful CPU or GPU at deployment, then there's another neural network architecture called the mobile net that could perform much better. So I hope to share with you in this video how the depth-wise separable convolution works. Let's first revisit what the normal convolution does, and then we'll modify it to build the depth-wise separable convolution. In the normal convolution, you may have an input image that is some n by nc, where nc is the number of channels, so 6 by 6 by 3 channels in this case, and you want to convolve it with a filter that is f by nc, and in this case is 3 by 3 by 3. And the way you do this is you would take this filter, which I'm going to draw as a 3-dimensional yellow block, and put the yellow filter over there. There are 27 multiplications you have to do, sum it up, and then that gives you this value, and then shift the filter over, multiply the 27 pairs of numbers, add that up, that gives you this number, and you keep going to get this, and then this, and so on, until you've computed all 4 by 4 output values. We didn't use padding in this case, and we used a stride of 1, which is why the output size, n out by n out, is a bit smaller than the input size. That is 4 by 4 instead of 6 by 6. And rather than just having one of these 3 by 3 by 3 filters, you may have some NC prime filters. And if you have 5 of them, then the output will be 4 by 4 by 5, or n out by n out by NC prime. So let's figure out what is the computational cost of what we just did. It turns out the total number of computations needed to compute this output is given by the number of filter parameters, which is 3 by 3 by 3 in this case, multiplied by the number of filter positions, that is the number of places where we place this big yellow block, which is 4 by 4, and then multiplied by the number of filters, which is 5 in this case. And you can check for yourself that this is the total number of multiplications we need to do, because at each of the locations where we plop down the filter, we need to do this many multiplications, and then we have this many filters. And if you multiply these numbers out, this turns out to be 2,160. So we'll come back. You'll see this number again later in this video when we come up with the depth-wise separable convolution that will be able to take as input a 6 by 6 by 3 image and output 4 by 4 by 5 set of activations, but with fewer computations than 2160. Let's see how the depth-wise separable convolution does. Does that. In contrast to the normal convolution which you just saw, the depthwise separable convolution has two steps. You're going to first use a depthwise convolution followed by a pointwise convolution. And it is these two steps which together make up this depthwise separable convolution. Let's see how each of these two steps work. In particular, let's flesh out the details of how the depthwise convolution, the first of these two steps, works. As before, we have an input that is 6 by 6 by 3, so n by nc, 3 channels. The filter in the depthwise convolution is going to be f by f, not f by f by nc, but just f by f. And the number of filters is going to be nc, which in this case is 3. The way that you will compute the 4 by 4 by 3 output is that you apply one of each of these filters to one of each of these input channels. Let's step through this. First, let's focus on the first of the 3 filters, just the red one. I'm going to take the red filter and position it there, carry out the 9 multiplications. Notice there's now 9 numbers you need to multiply, not 27, but 9, and add them up, and that will give you this value. Then shift it over, multiply the 9 corresponding pairs of numbers, that gives you this value. Over here, gives you that, and so on, until you get to the last of these 16 values. Next, we go to the second channel, and let's look at the green filter. The green filter, you position there, carry out the 9 multiplications to compute this value, shift it over by 1 to compute this value, shift it over by 1, and so on. And you do that 16 times until you've computed all of these values in the second channel of the output. Finally, you do this for the third channel. There's the blue filter, position it there to compute this value, shift it over, shift it over, shift it over, and so on, until you've computed all 16 outputs in that third channel as well. The size of the output after this step will be n out by n out, 4 by 4, by nc, where nc is the same as this nc, the number of channels in your original input. Let's look at the computational cost of what we've just done. Because to generate each of these output values, each of these 4 by 4 by 3 output values, it required 9 multiplications. And so the total computational cost is 3 by 3 times the number of filter positions, that is the number of positions each of these filters was placed on top of the image on the left, so that was 4 by 4, and then finally times the number of filters, which is 3. Another way to look at this is that you have 4 by 4 by 3 outputs, and for each of those outputs, you needed to carry out 9 multiplications. So the total computational cost is 3 times 3 times 4 times 4 times 3, and if you multiply out these numbers, it turns out to be 432. But we're not yet done. This is the depthwise convolution part of the depthwise separable convolution. There's one more step, which is we need to take this 4 by 4 by 3 intermediate value and carry out one more step. The remaining step is to take this 4 by 4 by 3 set of values, or n out by nc set of values, and apply a pointwise convolution in order to get the output we want, which will be 4 by 4 by 5. So let's see how the pointwise convolution works. Here's the pointwise convolution. We are going to take the intermediate set of values, which is n out by nc, and convolve it with a filter that is 1 by 1 by nc, 1 by 1 by 3 in this case. Well, you take this pink filter, this pink 1 by 1 by 3 block, and apply it at the upper leftmost position, carry out the 3 multiplications, add them up, and that gives you this value. Shift it over by 1. Now, so with 5 of these 1 by 1, let's figure out to a 6 by 6 by 3 input and wound up with a 4 by 4 by 5 output. And 160 convolution was about 31% as computed.
Quên cam.
Expensive as the normal convolution, so roughly a 3x savings. The authors of the MobileNets paper showed that in general, the ratio of the cost of the depthwise separable convolution compared to the normal convolution, that turns out to be equal to 1 over nc prime plus 1 over f squared in the general case. And in our case, this was 1 over 5 plus 1 over 3 squared, or 1 over 9, which is 0.31. In a more typical neural network example, nc prime will be much bigger. So it may be, say, 1 over 512 if you have 512 channels in your output plus 1 over 3 squared, would be a this would be a fairly typical parameters in a neural network. And this is really small, and this is 1/9. And so very roughly, the depth-wise separable convolution may be about 1/9, or maybe rounding up roughly 10 times cheaper in computational costs. And that's why the depth-wise separable convolution as a building block of a convnet allows you to carry out inference much more efficiently than using a normal convolution. Now, there's just one more detail I want to share with you before we wrap up this video. In the example that we went through, the input here was 6 by 6 by NC, where
Điểm cơ 2 mà. Không cần phải thế không trời?
where NC was equal to 3, you would also look a little bit simpler later from our PV filter. The depth to make some of the diameters by convolution. Just one more detail I want to share with you more efficiently. Maybe in general, the ratio of the 1/5 plus 1/3 squared, or 1/9, which is 0.3. Example that we went but it can be done at much lower computational cost. Let's now take this building block and use it to build the mobile net. We'll do that in the next video. Welcome back. In the last video, you learned about the depthwise separable convolution. Let's now plug this into a neural network in order to build the mobile net. The idea of mobile net is everywhere that you would previously have used an expensive convolutional operation, you can now learned about in the ResNet videos, and this residual connection or skip connections. But this is a paper published by Mark Sandler. Video I want to share with you one more improvement on this Sandler's and his colleagues that made mobile net work even better. which is why your inputs goes from n by 3 to n by 18. And that's why we call it an expansion as well. It increases the dimension of this by a factor of 6. The next step is the same dimension. In the last video, we went from 6 by 6 by 3 to 4 by 4 by 18 dimensional filter. And if you have, say, 3 filters, step, we will increase the size of the representation within the bottleneck block. And so this allows the neural network to learn a richer function. There's just more computation over here. But when deploying on a mobile device or an edge device, you will often be heavily memory constrained. And so the bottleneck block uses the pointwise convolution or the projection operation in order to project it back down to a smaller set of values so that when you pass this to the next block, the amount of memory needed to store these values is reduced back down. So the clever idea, the cool thing about the bottleneck block is that it enables a richer set of computations, thus allowing your neural network to learn richer, more complex functions, while also keeping the amounts of memory, that is the size of the activations you need to pass from layer to layer, relatively small. And that's why the MobileNet V2 can get a better performance than MobileNet V1, while still continuing to use only a modest amount of compute and memory resources. So putting it all together again, here's our earlier slide. MobileNet found which is efficient nets. Let's touch on that idea very briefly in the next video. Neural network architecture. The authors of the where the input image has a certain resolution R, and your neural network has a certain depth, and the layers has a certain width. The authors of the EfficientNet paper, Ming-Hsin Tan and my former PhD student Kwok Ler, observed that the 3 things you could do to scale things up. The authors of this has a certain baseline where the has a certain do so. Let's say you have a baseline has a certain the efficient paper Ming-Hsin Tan and
Scalable feature learning. Yeah. Ooh.
And my former PhD student, Kwok Ler, observed that the three things you could do to scale things up or down are you could use a high resolution image, so a new image resolution R. And I don't know how to denote a high resolution in a video like this, so I'm using this blue glow here to denote maybe high resolution image. Or you could make this network much deeper. So you could vary D, the depth of the neural network, or you can make the layers wider. So you can also vary the width of these layers. So the
Cơm muối ạ. Hát xì quá, kinh thật.
question is, given a particular computational budget, what's
Cái này cũng hơi cũ rồi. Thôi ha.
The computational budget, what's a good choice of R, D, and W? Or depending on the computational, what's a good choice? The scale up of the, if you want to scale up R, D, and W, what's the rate at which you should scale up each of these? Should you double the resolution between R with open source implementations of EfficientNet? Well, EfficientNet, you can also look.
Gì đấy?
Look at one of the depth resolution of the image and the depth and the width of the neural network. Now the tricky part is D and so you can also vary the width D, the depth of the neural network, or you can make the layers wider. So you can also vary vector width, I hope this will open up a lot of possible applications that you may now be able to build.
Cốt nha, cốt nha. Không biết thực ra có gì nhưng mà cứ làm thế cho nó nhẹ máy. Chơi mục tiêu hơi ác rồi anh em ạ. Thế mình chưa gạch được ạ. Bí thật đấy. Cốt cho cốt. Tôi học tiếp. Không thì ấy cũng... Gì trời. Nghe biết sao? Thôi đừng xóa hết anh em. Nói chung là code mà không có data xong rồi ngồi gõ bừa, nói chung là nhiều thứ bất cập lắm anh em. Nhiều thứ bất cập. chia. Chia flow ra. Đâu? Ây, mèo trốn rồi anh em. Gì rồi? À. Thế nên là đừng tham quá anh em. UP cũng có giới hạn của nó. Từ thôi nhá, miễn cứ từ từ thôi, vội chết sớm. Gì vậy? Gem à? Trời, lâu thế. Nói chung là phải hiểu cái này. Tôi phải lâu lâu nó mới check một phát này. Alo alo. Alo alo. À, từ từ nhá. Nếu thế thì cái này còn chạy không? Alo alo. À, thú vị ha. Hai tư 2048 40 096. Thôi, không hiểu gì luôn mà. Thiết. Why this if I think? Đấy thì chắc có hiểu rồi. Cái này mà chưa hiểu đây. Hello. Chắc là chạy cái quỷ kia nó ấy memory. Tôi không lag mà video lại lag à? Nào đây. Bình thường là ngược lại. À đâu, ấy là tôi lag khá là video lag rồi. Đi đâu vậy? Đọc hiệu suất thấp rồi. Chiến đấu với anh em ơi. Inverter. Đánh trở. Nên dùng database không? Tôi vẫn không nghĩ là nên database. Cho nó nhót rồi. Cái này không có xài được. Ok, ok, tôi nghĩ là chắc là phải dùng database thôi anh em ạ. Có lẽ database là ý hay. Có lẽ. Connect data and plot. Điêu thật chứ. Quá điêu. $60.000 đó thôi. Đã sắp chỉ cần thậm chí Windows size cố định cũng được. Size nó Cái gì đấy? À, just thinking. 60.000 đồng một kg. Đường quỷ thật. Thôi vào. Bật chế độ nói điều lên làm bài cho hiệu quả nhé. Hơi hiệu quả nha. Được rồi, chung là thêm cái đấy qua thôi. Đánh giá nhá, cốt như đang nhào. Tôi sai cả đâu? Có. Đâu sai mấy đâu sai, cái này không cần này. Audio đang ra không cần đi nữa đâu. Không hết, lúc nào nó chẳng không hết đúng không? Thế lỗi tính sau nhé. Được rồi. Nếu Windows sai cái này là cái cần thiết, cần phải pass lên. Thế cho nó có limit. Cái này ngoài data ra. À, đây, ở như đây đoạn này init đúng không? Thì mình gọi cái cell.plot ra. Đây con này không có data à? Nó chỉ data title nhá. Sao lại subplot rồi? Chắc thành chạy không ra rồi. Tiếp. Separator default này. Rồi, bắt đầu từ này này. Windows size. Whoa, 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 whoa. Alo. Ok. Mình vẫn vào là tốt rồi. Which vâng. Thế Wow. Chị ba, nhiều mic quá anh em ơi, không ổn rồi. Lại còn cái quỷ này nữa. Ấy da, thực sự là ấy da. Tôi nghĩ là tôi biết lỗi ở đâu đấy, nhưng mà làm sao sửa? Lại còn đạp mẹ cái dây sạc ra hả? À, Quỳnh ra đấy. Giờ tôi em biết cả biên học rồi còn phức gì nữa. Nói thật thì học thì khó, nhưng mà cái quỷ này thì audio stream xem nào nhá. Alo, không phải hả? Không phải. Để mình check. Alo. Wow. Đây, thì là ok, thế thì chúng ta có vấn đề rồi nữa. Là khi tôi chọn cái này, khi tôi chọn cái này đúng là cái này rồi. Cứu trời. Không, cái này cho nó có rồi. Đây, từ như này. Cái này thì phải có. Cái này thì sao? The fuck? Ok. Shiva. Cái này là sao trời? Thôi, nó rút cái này ra biết là gì phao rồi. Nói thật. Ý là ừm, ừm.
Have you seen this video?
It's only update.
This is pop 3. Let's assume he pays this person $25 an hour. There's 8 that pay this person $219,000 a year. Yeah, probably not. Number 2, he's scraping the views from YouTube. Then he has some sort of bot which updates the title every 3 minutes or so. Probably not. Any Google site would be incredibly hard to scrape and manipulate like that. So number 3, how he actually did it. There's these things called APIs, or application programming interfaces. Basically, it allows us to interact with Google services. For example, updating a YouTube video, but not through the browser, with code. And I've done the same thing with this video. I signed up for the Google API, I wrote about 50 lines of code, and I hosted that code on my favorite hosting platform. And that's it. The title of this video should be the exact amount of views that this video has.
Có lẽ là tôi cần restart máy nghe. Khó nói. Không ai ấy là gì đâu mà. Là Văn chat rồi Nghỉ. Suýt thì nhót. Một đất cua chưa? Hơi vội phải. Nếu không ăn thì mình có thể lấy tự ăn về. Ôi rồi. Nói chung là đang ấy anh em. Đấy. Chung là cần restart máy rồi. Vấn đề. Thôi thì stream hôm nay đến đây cũng đã dài rồi. Mai tôi cứ nào nữa là chẳng qua là có gặp một số vấn đề thôi. Chung là tôi sẽ sửa nó trong tối nay thôi. Mai lại live tiếp, mai học cái khác thì chắc không lỗi nữa. Ok nhá, bye bye. See ya. Actually mình check một tí đây. Anh làm được 2 việc nhá. Feature test code flow. Code flow. Có code flow rồi nhỉ? Lúc gan chưa làm, tôi sẽ có thay một content khác. Không được, gan phải làm chứ. Đó. Cố nốt xong cái này đi. Rồi. Ok, một cái Gemini cũng hay. Ok nha, chắc là tôi xin phép đi nha. Bye bye.